In part 2 of these videos, we'll be having a look at the circuit and how we can derive values for those constants of integration and therefore produce a final equation for the step response of our second order low-pass filter. A reminder that what we got from the last video was a general form for the step response of a second order system like this in terms of the poles P0 and P1 and three constants of integration. All we have to do is work out what those constants of integration have to be for any particular circuit. Well, the first thing we know is that you cannot change the voltage across a capacitor instantly. And we know the voltage across the capacitor was zero before the step arrived, because the voltages and currents everywhere were zero before the step arrived. So the voltage across the capacitor must be zero just after the step arrived as well, which tells me that x of 0 just after the step arrived must be 0. And if I substitute in t equals 0 into these expressions here, I would get that x of 0, which we know must be 0, is a plus b plus c. That's the first equation. I also know that at infinite time, after everything has settled down, the capacitor will have charged up to 1. At that point, there will be no potential difference across the resistor, so no current flowing, no change of current across the inductor, so no voltage across the inductor. Everything will have stabilized, and the final value will be 1. I could also get that from the final value theorem looking at the frequency response. Therefore, I can write x at infinity is equal to 1. Now, substituting infinity for t into this expression, noting that our poles are going to be negative, means that this is going to be e to the power of a very large negative number, or effectively 0. And the same thing is going to happen here. So this value of the output gives me that 1 must be equal to a. A plus b times 0 plus c times 0 is just a. So I know what a is. I've got two equations in three unknowns. Not enough to solve them. I need another equation. In this case, this is my third equation that I can use. The rate of change of the output at time t equals 0 must also be 0. I can't get that from the initial value theorem or the final value theorem. I have to do a bit of thinking to work out why that must be true. And it comes from the equation of the capacitor. The current through a capacitor is equal to C times the rate of change of the voltage across the capacitor, which is just dx dt in this case. Now, you cannot change the current through an inductor instantly. And we know the current through the inductor just before the step arrived was 0, so the current through the inductor just after the step arrived must be 0 as well. So my current at 0 is 0. Well, if that's true, then the value of dx dt at time t equals 0 just after the step must be equal to 0 as well. So I can write my third equation, dx dt evaluated at x equals 0 must be equal to 0. Put that into here, differentiate this expression, and I would get P0 b e to the P0t plus P1c e to the P1t. That's dx dt. And at t equals 0, this term here is just e to the power of 0, or 1. This term here is also e to the power of 0, or 1. So I would just end up with P0b plus P1c must be equal to 0, because that is dx dt evaluated at t equals 0. So I now have three simultaneous equations in three unknown constants, a, b, and c. I can solve that. It's not too hard a derivation to do. I'll just take this equation here, substitute in a equals 1. I'll get 1 plus b plus c equals 0. From this equation here, I can get that b is equal to minus p1c over p0. Substitute this into here, I'll get 1 minus p1c over p0 plus c equals 0. So, c of p1 over p0 minus 1 is equal to 1, or c p1 minus p0 all over p0 equals 1, which gives me c equals p0 over p1 minus p0. And an exactly similar analysis would give me b equals p1 over p0 minus p1. So I now have values for each of my constants of integration. I can substitute them into my general expression here and get the final step response of my second order low-pass filter. It's written in terms of the poles, but I can always calculate the poles from the resonant frequency and the Q factor using this standard formula. Just as we did with the frequency response, I now want to have a quick look at some special cases. And we'll start off with the same special case as we did with the frequency response, the case of very small Q factors, where the two poles are both real and of quite different values.